Now we're going to talk about multiple analysis. Suppose 20 null hypotheses are true. Each test has a 5% chance of being significant at the 5% level. That's what alpha being 0.05 means. Results this extreme occur only 5% of the time just by chance when the null hypothesis is true. So we would expect that 1 out of 20 tests to give us a significant result just by chance, because 1 in 20 is 5%, or the alpha of 0.05. Now, running one test and reaching the alpha 0.05 level of is reasonably good evidence against the null. If I ran 20 tests and reached the level only once, that's not. So we could also talk about confidence levels. The probability that all 20 95% confidence intervals will capture the true mean is much less than 95%. Now we're going to talk about planning studies, choosing the sample size for a confidence level in which we want a specific margin of error. So in these problems, you're going to be asked to find the sample size such that a particular confidence level will have a particular margin of error. This is the formula that you would use. The sample size equals Z0 times sigma divided by the margin of error, and we're going to square that quotient. So you will not get an integer when you do this. Therefore, your answer for your sample size, you need to go to the next greatest integer. So even if my answer was 12.01, I would need a sample size of 13 in order to get that particular confidence level with that particular margin of error. So let's take a look at this example again of the NAEP quantitative scores from Chapter 14. We want to use a 90% confidence interval, but we want to do it in such a way that the margin of error is no greater than 3 points. In that problem, recall that the population standard deviation was 60. We need to calculate the sample size that will be required in order that we get this 90% confidence interval with a margin of error no greater than 3 points. So what you would do in your formula for your critical value, remember for a 90% confidence interval, our critical value is 1.645. We're going to take that number, multiply it by the population standard deviation, and divide it by that margin of error we're asked to be within. We take that, we square that quantity, we get 1082.41. But remember, we can't have 1082.41 in our sample, so we go to the next greatest integer. So the sample size would be 1,083 men, would ensure that we would have a 90% confidence interval with a margin of error no more than 3 points. Let's take that same example and do it for a 95% confidence interval. How large would our sample size have to be for a 95% confidence interval to be within 3 points? Well, we know our critical value for a 95% confidence interval is 1.96. Our standard deviation isn't going to change, the population standard deviation of 60, and divide that by 3. When you square that, you get 1,536.64. We go to the next greatest integer, so our sample size is 1,537. That would ensure a 95% confidence level with no more than 3 points as a margin of error. Taking that same problem and looking at the 99% confidence interval, look how much that. We'd have to have 2,653 men in order to have a 99% confidence level not to exceed 3 points. Now we're going to talk about different errors that can occur in a significance test. And from here we'll understand what alpha is and why we use that, our p-value, we compare our p-value to our alpha. Now if we reject the null hypothesis when in fact it was true, so we're saying this is called a type 1 error. If we decide there is a significant relationship in the population, we reject the null hypothesis. This is an incorrect decision only if H0 is true. Now the probability of this incorrect decision is equal to alpha. That is the probability of rejecting the null hypothesis when it was true, that's That's a type 1 error. The probability of that type 1 error is alpha. So we want to minimize alpha, and our most common alphas are 0.01 and 0.05. Error. If we fail to reject the null hypothesis when in fact the null hypothesis was false, or another way we could say that is that the alternative was true, this is called a type 2 error. Now if we decide not to reject chance and thus allow for the plausibility of that null hypothesis, this is an incorrect decision only if the alternative is true. The probability of this incorrect decision is computed as 1 minus the power of the test. So another way to look at this is to use this diagram. It makes it kind of nice to see, a nice visual. Now on the top is the truth about the population, that which is true. So H not being true, two things that could happen in a hypothesis test is that our null hypothesis is true, or that our null hypothesis is false, which means our alternative is true. Now the decision we make is what we see vertically. We could either reject the null hypothesis or accept the null hypothesis. Now looking at both of these together will tell us whether we did an error or not. So if H naught is true and we rejected it, we have a type 1 error. Because it was true, we rejected it, we made an error. That's a type 1 error. If the alternative was true and we rejected H naught, we've done nothing wrong. We said it was false, and it was. Now if we accept the null hypothesis and it was true, then again we've done a correct decision, nothing wrong. But if we accept the null hypothesis when in fact the alternative was true, we've done a mistake. That's called a type 2 error. Now we're going to look at these errors in practice, well, practice for class. Let's look at this first one. The null hypothesis equals 3. The alternative is that we think the mean is less than 3. You reject the null hypothesis when in fact the mean was 2. Did you make an error? If so, which one, a type 1 or a type 2? Well, let's look at this. We rejected the null hypothesis. Two things could happen. Either we'll have a type 1 error, and remember what that is. A type 1 error is the probability, when we reject the null hypothesis when in fact it was true. So, was it true? Well, our mu is 2. So, we rejected the null when we should have, so we didn't make an error. Let's look at the second one. If the mean is 22, and our alternative says that the mean is greater than 22, we rejected H naught, when in fact the mean was 22. Did we make an error, and if so, which one was it? Well, the mean was 22, yet we rejected it. We said that it wasn't. We said that the null was false. So we did make an error, and we made a type 1 error. Let's look at our third case here. The null hypothesis says the mean is 32 versus the alternative, which says our mean is less than 32. I do not reject the null hypothesis when, in fact, the mean was 32. Did I make any errors? No. Because the mean was 32, I didn't reject it. Yahoo, I did the right thing. So let's look at the very last one. If the mean was 14, and that's my null, we think the mean is 14 versus the alternative where we're saying the mean is less than 14. I don't reject the null hypothesis. Somehow, with my significance level, I do not reject the null hypothesis. However, I find out the mean was 12. That means I said that the null was true when in fact it wasn't. I have done a type 2 error. And to finish off, we're going to talk about what exactly is alpha, that thing that we use as our basis to reject the null hypothesis. Well, alpha is the probability of rejecting the null hypothesis when it's true. So in other words, alpha is our probability of a type 1 error. So why is it that we reject the null hypothesis when our p-value is less than alpha? Well, that's because the p-value, another way to look at it, it's the probability of a type 1 error based on our sample. So if our sample is telling us that the probability of a type 1 error is less than what we were willing to accept, we feel comfortable to reject the null hypothesis. So this concludes Chapter 15.